everyone. Welcome to join today's programs. My name is Huang. I'm going to be a hoster for today's presentation. In today's presentation, we invited three excellent young speakers to talk about advanced emergent electronic devices. I would like to first introduce the first speakers. The first speaker is Professor Yang. He is an Associate Dean of the Faculty of Science of the Hong Kong Polytechnic University, Vice President of the Physics Society of Hong Kong, a member of the Hong Kong Young Academy of Science, IEEE Distinguished Lecturer since 2016, and the Vice Chair of IEEE EDS Region 10, and he was the Chair of IEEE SSC Hong Kong Chapter. He is a recipient of the RGC Early Career Award in 2014, the Semiconductor Science and Technology Early Career Research Award in 2017, and the Polytech FAST Faculty Award in Research and Scholar Activity in 2019 and 2018, the Young Scientist Award of ICON 2D MET in 2019, the Polytech President Award in Research and Scholar Activity in 2019 and 20. He also an R45 Young Investigator Award in 2021. He also won several other very prestigious awards. His current research interests mainly focus on emergent electronic devices. So in today's presentation, he will talk about in-sensor computing for artifact vision. Let's welcome Professor Yang for today's presentation.
Okay, thank you very much, Professor Huang. So let me share my PPT slides. Can you stop your sharing?
Yeah.
Okay, so let me start my share. Can you see my PPT slides?
Yes, I can see your slides.
Okay, so it's really my great pleasure to attend this ICANN Young's talk. So this is Yang from Hong Kong Polytechnic University. Today I'm going to share our latest research study. The title of my talk is In-Sensor Computing for Artificial Vision. First, let me give a very quick introduction to the background of this research. We are living in the big data world. So every second it generates a huge amount of data. For example, in the physical world, every second it generates 10 to 34 bits per second. We also have a lot of sensor. We are developing Internet of Things. We have a lot of sensor. These sensors actually are bridge between the physical world and the electronic world. So it rapidly increase number and generate huge data. But for our human person, our perception capability, it is very limited. And in the past 1,000 years, this perception capability didn't increase. So there is a huge gap. That means a human person actually lost a lot of information from the physical world. But we can still survive in this very complicated world. The reason is that our human sensory organ can efficiently filter the useless data. Although the data amount is huge, but most of data actually redundant, useless. It doesn't help us to understand this physical world efficiently. So human sensory organ actually, they are not a simple sensory device. They can also do some computation, so that can help us to extract most useful information and help us to understand the surrounding environment. So let's go back to see the conventional sensory computing architecture. Previously, sensor is sensor, computing is a computing unit. Sensor typically generate analog data, but in computing unit, we handle digital signal. So we have to transfer the data between the sensor and the computing unit, and we also do the analog to digital conversion. So when the data amount is few, it doesn't matter too much. But when the data is huge, the data transfer and the data conversion become a very huge problem. It will cause a lot of power consumption and time delay. So it's a very straightforward way to shift part of the compute functionality from the central computing to more close to the sensory terminal, because the sensory terminal it generates the data. So people develop the so-called near sensor and in-sensor computing. Near sensor computing actually is not new. People just use some packaging technology, use advanced microfabrication technology to reduce the physical distance between the sensor and the computing unit. So people can reduce to hundreds of micrometer, even hundreds of nanometer. So there are already some prototype and even commercial products. But for the in-sensor computing, this is relatively new. People use in some multifunctional device. And this device, they can work as a sensor. They can also work as a computing unit. So when we connect a multiple sensors together, they can execute some computation tasks. So just now, I show you we can divide the sensory computing as a near sensor and in-sensor computing. Depends on the physical distance between the sensor and the computing unit. If we classify the in-sensor computing from the functionality, we can divide as a low-level and a high-level in-sensor computing. For the low-level in-sensor computing, it just convert the unstructured information into some featured information, and then it will help us to understand the feature much easier. High-level computing actually is more abstract. For example, if we can construct some neural network, we can directly classify the object. If the object is static, we can recognize it's a banana or apple. If there is a motion, we can recognize its movement direction and movement speed. So low-level in-sensor computing actually we just make the unstructured data with enhance its feature and reduce the noise. So here we can use the different response characteristics of the sensor. The sensor can be superlinear, it can be sublinear at the threshold. So it depends on different response characteristics. We can do different low-level in-sensor computing. For example, a few years ago, our team designed and fabricated the so-called optoelectronic random access memory. This device has a superlinear response characteristics. We can use it to enhance the image contrast of a static image. For some sensors, they have a sublinear response characteristics. We can also use it to increase its dynamic range and compress the spatial temporal information and perceive the dynamic motion. So today, my research talk mainly will talk about the sensor with the sublinear response characteristics. First, let me give an example how to use the sensor to do the vision adaptation. A very quick background. In the nature environment, actually, the light intensity distribution is very broad. It could be very dark, it could be very bright. The range actually can be over 160 dB. But when we use our camera to take a picture, if the background is too bright, too dark, it's difficult to take a high quality image. That is because in our camera, it is made with silicon pin diode. For the silicon pin diode, its dynamic range it's only around 60, 70 dB. Of course, you cannot take a high quality image. You use very narrow red photodetectors. But for our human retina, it's different. In the retina, we have a photoreceptor. In the photoreceptor, we have a root cell that can detect dim light, and a core cell that can detect bright light. But their dynamic range actually is also very narrow, just 40 dB, and even smaller than that of silicon pin diode. But in the human retina, we have another cell that is horizontal cell. Horizontal cell actually can control the ratio of the root cell and the core cell on the different lighting condition. That we can do the adaptation. For example, when we go inside a cinema to see movie, originally it's very dark, we cannot see anything. But if you stay there for a few minutes, you can gradually see the environment more clearly. This is a adaptation process. So just now I talk about the adaptation in the biological vision system. Actually, we have two mechanisms. The first mechanism is the quick adaptation. So we can use a horizontal cell to control the ratio between the root cell and the core cell. The second mechanism actually it is about the regeneration and blinking of the photopigment in the human retina. This involves some photochemical reaction. This process is relatively slow. If we are going to use electronic device and optical electronic device to emulate this vision adaptation process, we need to adjust the response characteristics in both directions. It can be excitive, it can be inhibitive under the same conditions. But it is not an easy task. For most of electronic device, it can be only to you along one direction if the lighting condition is fixed. So here, people actually already use some circuit design technology to realize this vision adaptation function, but their mechanism actually is not similar to the biological. They encode the light intensity to tray of the power. The frequency of the power tray is proportional to the light intensity, which is very different from the human retina. So in our team, we try to use a simple device to emulate the function of the human retina. So here we choose to use a 2D semiconductor. 2D semiconductor is indeed a very hot research topic, but it also has some unique physical property. For example, it's very thin. If you apply the gate voltage, you can efficiently to modulate optical electronic activity for a large range. And also, its surface to volume ratio is pretty large. So the charge trapping density at the interface could be even close to the carrier concentration in the channel. So this unique divided physics also allow us to do the vision adaptation. So here we collaborate with Professor Zhong at Yonsei University in Korea. So their research team can grow very high quality, a large area 2D semiconductor C film. So we get this sample from their team. You can see the spectroscopy, morphology, its uniformity actually pretty good. We fabricated a 10 by 10 photo transistor. It shows some variation, but this variation is still reasonable. It doesn't affect the subsequent vision adaptation functionalities. After we fabricated the phototransistor array, we did the optical electronic characterizations. So we characterize the single device on the different light intensity with a different gate voltage. So here you can see with the increase of light intensity, the photo counter actually shows a sublinear response characteristics. Here we also define the photosensitivity. This figure shows the photosensitivity as a function of the input light intensity. So under different gate voltage, the photosensitivity actually change over a large range. For example, if the gate voltage is positive, the sensitivity actually is pretty low. If the gate voltage is negative, the sensitivity could be very large. So here we can extract its efficient dynamic range. It's over 190 dB. It is much higher than that of silicon pin diode. So here actually we can use a gate voltage to control its photosensitivity to change over a lot of orders. So at positive gate voltage, the same device works like a co-cell. But if we use the negative gate voltage, the device works look like a root cell. So there is a very famous law that is Weber-Fechner law. It is defines the relationship between the external stimulation and the inside perception. So basically here we also define the just notice photocurrent as the threshold. So we plant the threshold as a function of the light intensity. Actually, it matches very well with the Weber-Fechner's law. Also, we can use gate voltage to do the peak adaptation, but actually we can also use the charge dynamics of the interface charge trap to emulate the slow adaptation process. So here you can see it, if the light intensity is a constant, it continues illumination on top of the phototransistor. And then we apply negative gate voltage. You can see the photo current keep increasing. It shows the activation behavior. But if under the same lighting condition, we still use the continuous lighting. But if we apply to positive gate voltage, it shows the inhibition behavior. The physics mechanism actually is very straightforward. So here we just use gate voltage to control the barrier of the interface charge trap. If the negative gate voltage, the charge trap barrier actually is reduced. More carry will go inside the semiconductor channel. If we apply positive gate voltage, the barrier height actually is increased. So the photo count is decreased. So by combining the different gate voltage at the different light intensity, actually we can show we can use the same device to demonstrate the activation and inhibition. So that means we can do the vision adaptation in both directions. So we can decrease the sensitivity, we can increase the sensitivity. So it is very similar to the human retina that consists of both root cell and co-cell. So after we studied the single device, we characterize the 10 by 10 phototransistor array. So we can do the scotopic adaptation and the photopic adaptation. For the scotopic adaptation, at the very beginning, the background is very dark. We cannot see anything. But if we apply negative gate voltage to increase the photosensitivity, you can see the image automatically become clear and clear, so we can see it its shape. Similarly, if the initial condition is very bright, we still cannot see anything. But if we apply positive gate voltage to decrease the photosensitivity, we can also see the image more clear. So basically, this photosensor actually realizes the low-level in-sensor computing functionality. So the input data actually is unstructured, but after the pre-treatment with our photosensor, its feature become more obvious, so we can see its shape more clearly. So if the unstructured data is converted into featured data, and then we feed this featured data into a very simple artificial neural network. For example, just 3 layer. So actually, we can recognize the image very easily. That means we can save a lot of computation resource. So you can see with this vision adaptation process, we can easily realize over 90% recognition accuracy. Even the background is very dark or the background is very bright. So this is the first work I show you today. The second work is still about the low-level in-sensor computing. We are still using the photosensor with the sublinear response characteristics. But in the second work, we are going to demonstrate to recognize the dynamic motion, not only the static image. So today, ChatGPT is very hot because its functionality actually is very powerful. Because the ChatGPT actually it is based on the artificial intelligence at the computation terminal. But in the in nature, actually, we also have an intelligent more close to the sensory terminal. At the sensory terminal, we don't have a large space. We don't have a high power to realize the high-level intelligence. So at the sensory terminal, we have to carefully define the neural architecture to realize the intelligence. So here I can show you an example. So for example, so when people try to sweat some flying insect, sometimes we can catch it, sometimes we cannot. But if we extract the motion speed, the sweat motion speed actually is pretty high. It's 50 kilometer per hour. But for the flying insect, its motion speed actually is relatively low, just 8 kilometer per hour. If we compare the motion speed, it should be very straightforward. It should be very easy for us to catch the flying circuit. But why sometimes we still fail? That is that is because of the in the flying insect, their vision system is more agile. If you look at the structure of the flying insect, it only has 800 photoreceptor at 10 to 5 neuron. But for human person, we have a 10 to 8 photoreceptor at 10 to 11 neuron. So from the number of this photoreceptor at the neuron, our human vision system should be more powerful. But why it's not agile as the flying insect? There are two major reasons. The first reason is that the distance in the insect vision system, the distance between their eye and the brain is very short. So the information transmission is very quick. For human, the distance between the eye and brain it is relatively long, so we cannot. The information transmission will take more time. The second reason is that the neural structure of the flying insect. In human vision system, the neural actually is a spiky neural, but in the insect vision system, the neural are graded neural. So from the graded neural, its information transmission rate actually is pretty high, over 1,000 bits per second, 5 times higher than spiking neural. And also, gradient neural actually it shows the analog behavior. Spiking neural shows the digital behavior. So from the analog device, we can do the multi-level coding. So the information coding capacity is much higher. So here, this slide, I can compare these two kind of neural. From the spiking neural, it's most like the digital behavior. Below the threshold, it's zero. Over the threshold, it's generate spikes signal with very high amplitude. But after we generate the spiking signal, there is a refractory period. In this refractory period, it cannot code in the information. So gradient neural is very different. So here we can show the multi-level response. We don't have a refractory period. So the coding capacity is much higher. Let's go back to the conventional machine vision system. Typically, we have two streams, spatial stream and temporal stream from the sensory terminal. So these two streams actually fuse in the computing unit. So, because of the information from these two separated streams are huge, so we also require very complicated neural network to do to do the information processing. But in the insect vision system, they are very different. Actually, they can use gradient neural to fuse the spatial and the temporal stream at the sensory terminal. So they can extract the feature from unstructured data and feed this unstructured data into simple brain, so they can still recognize the motion very efficiently. So here we still use the 2D semiconductor to emulate the functionality of gradient neural. In the 2D semiconductor, there is always some charge trap at the interface. So if we write the equation of a charge trap in dynamics, it is very exactly the same as that of the gradient neural. So here you can see 30 years ago, people already do the biological measurement to measure the gradient neural in the insect vision system. So you can see their response actually shows the sublinear behavior. And they can also do the multi-level coding. So here in our single device, we also do the similar test. Our device can also show the multiple level response at sublinear response. This means it has a very high information transmission rate. So how to experimentally to measure this information transmission rate? We first characterize the signal to noise ratio under different light intensity at a different frequency. So we can extract the SNR. Once we get the signal to noise ratio, we can use the Shannon equation to calculate the information transmission rate. So it's over 1,000 bit per second. If the light intensity is increased, the information transmission rate is also increased. So here we can use a single device to fuse the spatial and temporal information. We divide one motion with a phone frame. So actually, from single device, we can distinguishly it's 16 states. So these 16 states actually fuse the both temporal and spatial information. So here I can show you our experimental results. So you can see we fabricated 20 by 20 photo transistor array, and we try to capture the motion. We still use the sweat motion. It can move left, move left and move right, approaching and leaving. So this is a video. So let me show you. Let me show you this video. So you can see our experimental results. So actually, we can use this artificial grid array to record a movement. The trajectory actually is record with our vision sensors. So you can see the trajectory of the motion is clearly recorded here, and then we can feed into some very simple neural network. It will recognize the motion very easily. So the motion direction is one important parameter. The other important parameter is the motion speed. So if we still use the phone frame to do the encoding, uh, we, we also need to adjust its time constant to capture the motion with a different speed. So here we use the device is 3 terminal. We can still use the get one terminal to change the time constant, which can change over a large range. So here you can see if we try to catch high speed movement uh, without the get voltage, the time constant actually is relatively long. After a period, the trajectory cannot be recorded. But if we apply positive get voltage to decrease the time constant, the phone frame can still show the trajectory within a certain period. So here we can, in the same vision field, we can perceive both high speed and slow speed motion. Uh, so the slow speed motion can be regarded as some background noise. After we extract the feature from this motion, we can fit into a very simple neural network. So here we we generate some videos by ourselves. It's very simple. Just a ball is moving left to right, at the top to down. So then we can use this video to we can use our uh, vision sensor to process this video. So the video actually can be its trajectory motion can be well recorded. If we use conventional image sensor to record, it doesn't fuse the temporal information, so we don't know its trajectory. So if we feed into the neural network, so the probability from the left and right is the same. So the accuracy is just 50%. But here, if we use the ball inspired sensor, the trajectory is recorded. We can easily recognize the motion with a high accuracy. We can also recognize the motion with different speed. So, for example, snail move very slowly, cheetah move very quickly. We can just use different get voltage to change the time constant and catch the motion with a different speed. I think my time is almost done. So just give maybe 2 minutes to complete the briefly say a few words about the second part. For the high level in-sensor computing, actually, we can also realize by sensor array. So we can do the multiplication, we can do the summation. If we can use a sensor to do multiplication and accumulation, we can do most of the machine learning algorithm. So a few years ago, actually, we summarized these two equations from the in-sensor computing, high-level in-sensor computing. So Thomson Muller demonstrated some example to recognize the static image. At that stage, he still used a very small array, that's 3 by 3 device, 3 by 3 array. And the material system is still 2D semiconductor. But last year, Donghua Ham at Harvard University, they extend the same principle to the silicon technology. Silicon is very mature, so they can use the silicon technology to fabricate a large-scale photodiode array. they can realize the similar functionality, but the scale is much larger. So last year we also overview different kind of sensor. Some sensor with linear response we can use for the high level in sensor computing. Some sensor has a nonlinear response we can use for the low level in sensor computing. So from both Thomson Muller and Donghua Ham's case, they use the frame-based vision sensor. Actually, it generates a lot of redundant data. At last year at IEDM, we designed a event drive sensor with a very simple device. That's a 2T2R1C, which can generate event driving spikes. So we can build the so-called in-sensor spike in neural network. The data redundancy is significantly reduced. So last year, my another PhD student, Wan Jieqing, he write a review article in Advanced Material overviews the material device and integration from the in-sensor computing. And last year, we also edited a book in Springer and Nature. We overview the recent progress in this field. So here I will not repeat the summary of my talk. Most of my work are actually done by my students. The first work is done by Fu Liao, who is in Huawei right now. And the second work is done by Jie Chen. He is still in my team. So that's all for my presentation. Thank you very much.
Okay, thank you, Professor Yang, for his excellent work in sensor computing. There are many questions from me. I will wait for the discussion section to ask you the questions. Thank you again. Okay, next, I would like to welcome our next speakers, Professor Liu Jun from the State University of New York. I would like to briefly introduce Professor Liu. Professor Liu Jun is currently an assistant professor in the Department of Mechanical and Aerospace Engineering, the State University of New York at Buffalo. He is also an affiliate faculty of UB Renews Institute. Dr. Liu is also an associate editor of Energy Technology since 2023. He received his PhD in material engineering from the University of Alberta, Canada, with expertise on advanced materials and nanomechanics for energy harvesting. He is the recipient of many awards, such as 2022 Sony Faculty Innovation Award, 2020 Microsystem and Nano Engineering Young Scientist Award, and 2019 Best Scientist Research Award. He has 14 high-profile journal publications, such as Nature Nanotechnology, Science Advances, Matters, Nano Matters, and Advanced Functional Materials. And he also holds multiple US and PCT patents. He has been invited for talk in many professional conferences. Okay, let's welcome Professor Liu for today's presentation. The title of his presentation will be Mechanical Modulated Semiconductor Interface, Energy, Sensing, and Beyond. Welcome, Professor Liu.
Thank you. Thank you so much, Dr. Huang. Can you hear me well and see my screen well?
Yeah, I can see your screen. Yeah.
Wonderful. Thank you so much for having me for this wonderful platform. And then it's my great pleasure today to share you some of my past work based on the semiconductor system for energy, sensing, and other applications. So like Dr. Huang mentioned, I'm currently an assistant professor at University of Buffalo. So University of Buffalo, or UB, is part of the State University of New York system. And then here is where we are located at. We're located at the upstate New York, which is about 20 minutes driving from the world famous Niagara Falls. And then here on the right-hand side, I have two images of the Niagara Falls in the summertime and in the wintertime. So actually, this is associated with some of the contents we are going to talk about today. So here, I just want you to remind you a question about what is the potential energy and what is the kinetic energy of those two different cases. Okay. So the contents of my talk today will start from some of the fundamental observations at nanoscopic level, as well as the microscopic demonstration and fundamental mechanism study. And also we will talk about the practical applications of this new energy harvesting mechanism for flexible energy harvesting, pixel-based energy cell power sensing, and also we also extended for green chemistry recently. And then lastly, I'm going to talk about the tunable tribal electronics, or we call it tribotronics application with these new effects. So first of all, for those of you who are not familiar with tribal electricity, so this is an interesting example. You can see that the cat has all those foam bubbles on his body, right? And then we know that this is because of the attractive force due to the existence of tribal electricity. And then you can see that from high school physics, we know that when you rub two materials against each other, the materials might get positive or negatively charged, right? Depending on what kind of materials you have. And empirically, you can also find the so-called triboelectric series and then trying to find out what polarity of the charges you can carry, whether it's positive or negative, right? Like depending on the position of these materials on this series. And we also know that the triboelectric voltage can be extremely high, right? It can be as high as kilovolts. But the question is why, for example, this little kid here is still safe, right? And then also another example we can see on life is that when you take off your sweater in the wintertime, sometimes you can see the sparks, but you never hurt yourself, right? So basically, if you look at the contact interface, like we mentioned, you can generate positive or negative charges. And then the thing is that when you have an insulator involved in the system, which is most of the cases for electricities, we know that the charges are in the electrostatic form, right? And then the charges will stay on the surface, and which cannot be conducted throughout the system since the material is so insulating, right? And in order to generate power, and we know that power is basically the products of voltage and the currents, right? And then, of course, you can integrate this power as a function of time, which give you energy. But the thing is that even though this voltage can be high, currents cannot flow, but how can we make the current flow, right? So traditionally, what people do, people develop this concept called dielectric displacement currents, which means that they have a charged capacitor, for example. We know that the charged capacitor, the voltage and then capacitor will have a relationship, right? And then the capacitor depends on the thickness of the dielectric and also the area of the dielectric, right? And then once you oscillate these charged capacitor vertically or horizontally, and you can see that you're going to expect a time derivative of your voltage and capacitor, right? And as a result, you can get a peak currents in the AC form. So we call it triboelectric AC currents, right? But the thing is that this only happens like on the right-hand side when you have a changing voltage, right? And then the form of these currents is actually a transient pulsed currents, right? And then that means if you really integrate the products of voltage and current, which is going to be the power, there will be many times in this time domain which cannot give you power outputs. And also you can see that from this equation, you will know that the energy, the currents outputs depends on how fast you oscillate these systems, right? And then the more frequently you oscillate the system, the more power you can get. But however, we know that for most of the ambient vibration, for example, if you want to use that for energy harvesting, the most of the ambient vibration has a frequency less than 10 hertz. So those are some of the intrinsic, limitation of the traditional triboelectric generation. And our journey of studying semiconductor systems started from 2018 from an accidental observation. So, so one day when I was doing this conductive AFM characterization, what we found out that the sliding between a metal, and here we use a two-dimensional MOS2 system. So we find out that the sliding between these two material will generate a constant DC currents, right, from nanoscopic level. And then we found that these currents is and the voltage is very different from the previous AC one. You can see that it's always DC and also constants. And then here it is basically the difference between metal, semiconductor, and insulator, right? And I assume that most of our audience here has a background for a semiconductor. If not, the take-home message is that for insulator, it does has a large band gap. Well, the electrons cannot go unless you have surface states, right? For metals, basically the valence band, conduction band, between them, there's no band gap. And for semiconductor, this gap is relatively smaller compared to the insulator, right? And if you put the metal and semiconductor together, you can either form ohmic contact or Schottky contact, right? So for the ohmic contact, is basically give you a linear characteristic between a current and voltage. If apply voltage and measure currents, you're gonna see a linear relationship. But for Schottky contact, you can see a nonlinear features, right? And then for this feature, we call it a rectifying features, right? And then the fundamental reason is because for ohmic contact, there's no bending on the semiconductor side, but or if you have a really narrow depletion layer where the electrons can tunnel through, or and then in the case of a Schottky contact, you can see that there will be a bending, and then there'll be an energy barrier for electrons, for example, to go from metal to semiconductor side or from semiconductor side to metal side. So it turned out that this Schottky feature is the key to generate the DC phenomenon, because we do the in situ IV characterization on different locations of these MOS2, for example. And then the conclusion we have is that in order to generate DC, you have to form the so-called Schottky diode, right, with these rectifying features in order to generate this phenomenon. And then we have also done the semiotic emission model fitting to find out what is the ideal factor and the energy barrier for this physical Schottky diode. And then first physical image in our mind is that it might be related to some of the excitation of electrical pairs right at the interface, right? Since MOS2 is also a semiconductor materials, and then there might be some directional motion of the electrons with some mechanisms. At this point, we still have no very clear answers. And then the next question is it a common phenomenon for all the semiconductors, right? And then right after that, we prove that it can also be observed in other material, for example, silicon, right? We know that silicon is most commonly used semiconductors in the industry. And then you can see that also here is a nanoscale observation. If you increase the contact force, right, you can see that the current will also enhance as a function of force. And also you can find out what is the open circuit voltage in this case, right? So the way we do here is by apply bias of the opposite polarity and see at which bias the currents will be decreased to zero and reversed, right? And then in this case, it shows that the open circuit voltage is about 100 to 200 millivolts. So I'm going to show that this voltage has been improved significantly in the recent years. But however, if you look at the currents, you can see that here it's a macroscopic demonstration. So like we said that in the previous slides, we have been working on nanoscopic observation. But what if you have a macroscopic system, right? So what we did, you can just take a tester probe made of, for example, stainless steel from your lab and rubbing on the surface of, for example, a silicon wafer, right? And basically you measure the voltage or you measure the currents, short circuit currents, And then you can see that when you do linear motion back and forth, it's going to give you voltage and current at the same time, right? And then if you rotate your tip on the surface of this silicon, it's going to give you continuous voltage or current outputs. And you can see that the feature is very different from the previous AC one, since the currents and voltage output are in phase, right? And then if you calculate the current density, which is the currents normalized by the contact area, you can see that the current density is on the order of 1 to 10 ampere per meter square. And in comparison, we know that the state-of-the-art piezoelectric or triboelectric generators only gives you about 2-3 orders lower current density. So we know that for these special semiconductor system, the current output has a much higher currents, right? Even though the voltage is relatively lower compared to the case. And then we propose and also in the silicon case, we propose this mechanism that you have the generation of the electrical pairs, and then it's probably get through this barrier and get conducted by the conduction band or valence band, depending on whether you have an electron or holes in the system. And another thing we would like to emphasize, since this is DC, you don't really need a rectification in your circuits. For example, here in this video, we show you the voltage of a capacitor right here, a charging capacitor, by simply rubbing a stainless steel probe on the piece of silicon. This is actually very simple experiments everyone can do in a lab, right? And you can see that I'm rubbing it with a pretty low frequency, very gently, and then this capacitor can be charged continuously, right? And there's no rectification circuits in this case. So the next question is, how does the electron get through the system, right? Because we know that for traditional system, electrons will just stay on the surface. So here, in order to testify the hypothesis that electron does get through the barrier, we did atomic laser deposition on the silicon of oxide with some oxide, because we know that for any silicon, it has a native oxide thickness around 1 to 2 nanometer, as long as it's exposed to atmosphere, right? And then by using ALD, we would be able to control the thickness of this oxide and then measure the current outputs simultaneously, right? The outputs current simultaneously. So now we can see that with increasing oxide thickness, the output currents, the DC currents, will drop exponentially as a function of thickness. So this is actually in good accordance with the quantum mechanical tunneling mechanism, because we know that in quantum mechanical tunneling, that the probability of charges to get through an energy barriers follow this exponential law. So then from here we have a better, feeling that the electrons, instead of staying on the surface, they will actually quantum mechanically tunnel through the physical barrier. Since this is not a chemical bounding between the metal and semiconductor, just bear in mind, but they can quantum mechanically tunnel through it. And once it goes into the semiconductor, it can be, first it can be driven by the building electric field in the depletion area of the semiconductor, and it can be continuously conducted. So that's why, that's how the DC is formed. Like we said, that compared to traditional one, this is pretty much like the Niagara Falls in the winter time versus the summertime, right? Because we know that for the winter time, the water molecules are frozen, right? So you still have the potential difference because the height difference is still there, but the currents will be low because the whole system has a high impedance, right? So these water molecules, all the current in the system cannot flow freely. But in our case, if you have semiconductor, then the water can actually flow freely. That's pretty much like the summertime Niagara Falls. That's why we have this continuous high DC. And then further on, we have also extended the idea to, for example, the macroscopic sliding 2D material, right, with different structures, and then we find out that there were different mechanisms as well. If you have an oxide, for example, because for the conducting mechanism of semiconductor, oxide may also involve defects and surface states and many other things, and also we have trying to think that if this is associated with semiconductor, and then we also know that semiconductor is a very good photovoltaic materials, right? It can react to irradiation. So can we actually combine these two effects? So the answer is yes. So we also did this the irradiation experiments in the AFM system, and we did observe an add up of the current outputs with and without irradiation. And we know that without light, it does give you outputs, which is corresponds to the trivoltaic DC. And then in the under the radiation, you also see outputs. And then we also demonstrated with the silicon at the microscopic level. So here we demonstrate the idea with sliding ITO on a piece of silicon. We know ITO is a transparent conductive oxide, right? And you can see that both voltage and currents can actually be added up, right? So that means there's a synergetic effect between the trivoltaic effects and photovoltaic effects. And then so here, why we give a name of trivoltaic later on, so this is basically in analogy with photovoltaic effects, because we know that in a photovoltaic systems, the electron hole pairs are generated by irradiation from photon, right, in a semiconductor. But however, so this corresponds to the case right here, for example. And if you have a triboelectric DC generation, you can see that instead of generating electron hole pairs inside the depletion layer, we have this electron hole pair excitation right at the surface, right? So here we're actually converting mechanical energy into electron hole pairs, right? So that's why we say that it is very similar to a photovoltaic effects, and then we can also call this phenomenon of tribovoltaic effects, right? And then when you have this mechanical stimulation and irradiation together, you might be able to excite the electron hole pair simultaneously with mechanical energy and photonic energy. So later on, like we said, that it's pretty well known that's how an electron hole pairs are generated by photon, right? If you have a irradiation. But in terms of the exact mechanism that how these mechanical energy at macroscopic level are converted to the kinetic energy of an electron. So this is actually an untapped area, right? And then recently we have also done many fundamental physical study, which, for example, quantum dynamics approach. So this is a collaboration with Professor Wen Jido in Westlake. And then the hypothesis we have is that right at the contact interface, you might have many contact asperities. So this contact asperity usually has a size of tens of hundreds of nanometers, and then the local temperature right between those contact spots can be extremely high. So it can be as high as 1,000 K, right? Even though the apparent temperature of the material is not really high, it still stays as a room temperature, but the localized, the agitation of atoms at a single asperity is very intensive. And then we did the quantum dynamic calculation and trying to find out the population of electron and holes for a system, and then we find out that the phonon, which is the collective oscillation of this nucleus, right, can be converted into the energy of electrons. So this is called the breakdown of Born-Oppenheimer approximation. So basically, we know that in most of the cases, in an atom, the electron cloud will move with the nuclei, right? So in this case, so you don't have this energy transition, but however, you only have energy transition from one atom to another. And then if the atoms are in a lattice, you have the collective oscillation of these atoms, right? That's we call phonon, which is a quantum mechanical concepts of heat transfer, right? But however, in this case, if the nuclei move so fast, right, the electron cloud cannot follow the motion of this nuclei, and then in this case, it's the breakdown of Born-Oppenheimer approximation, right? And in this case, you can see there will be an energy transition from this nuclei to the electron cloud, or in physics, people call it electron phonon coupling, right? So, and then also the interesting thing is that even if you don't have that the macroscopic single asperity, but we know that for many 2D materials, for example, they also have this. They should have also have the fluctuation of surface potential on the surface. So why this one is important, because we know that's for like we showed in the very first slide, we tested on MOS2. but actually, before MOS2 become a fancy material for electronics, nanoelectronics, this has been long used for lubrication industry, for mechanical industry, right? So we know that people actually take advantage of the van der Waals force between those layer structures, which can lubricate your mechanical parts, right? So this is a very commonly used, very common applications. So the idea is, can we actually, can we actually, take advantage of this idea for energy harvesting, right? And then so here we showcase two examples. The first example is it's also a nanoscale demonstration, but with the graphites sliding on N-type silicon, and then we know that graphite is also have this layer structure, and between layer structure you have the van der Waals force. And then this is a work by done by Professor Chen Shui-Zheng's group from Tsinghua University. They did show a long cycles, more than 5,000 cycles of the rubbing between the graphites and silicon. They also observed this DC phenomenon, the same physics we were talking about. And then you can see that this DC generation is much stable, right? And then also you can see that there's a recent work here using hydrogenated diamond-like carbon films rubbing on also on silicon substrates, and you can see that, and they have down even 10,000 cycles. So different from the first paper here, you can see that this is actually a macroscopic demonstration, right? And then they, at the same time, they measure the coefficient of friction, which is less than 0.01, which is very low friction, but however, they can still generate this very constant DC outputs, right, in this system. And then, like we mentioned, the voltage of the semiconductor system is relatively lower than the insulator system. Like we know that, as we show here, so most of these voltage we show has a range of hundreds of millivolts, right? But some of the exciting developments recently, this is a work recently by Dr. Zhang from Chinese Academy of Science. You can see that with some very special material system, for example, we have this N-type gallium nitride system. The sliding between the metal and then gallium nitride can actually generate a surprisingly high DC voltage. This DC voltage can reach as high as 130 volts, right? I think this is a very exciting observation, and I believe that many new physics underneath as well, right? And then so here so those are the first parts of my talk. I have been talking about some of the fundamental physics we have been observing and some of the reasons observations from the community. And then for the second half, I'm going to switch to some of the practical applications, some of the efforts we have to develop devices for energy sensing, chemistry, and electronics. And then we all know that the future IoT, Internet of Things, and smart healthcare will be powered by this wearable and implantable electronics. And also, for industrial IoTs, it does need energy sources for structured health sensing and monitoring. And then this requires the flexible, miniaturized, scalable, and self-powered features, right, for these devices. So like we said, we have been working with inorganic materials, and would like to extend it to organic material system. So this is an example. We extended the idea from silicon to conducting polymer, and you can see that they will also very high current output actually from this flexible concept. It can generate as high as hundreds of microampere and approximately 1 volts. So that means we are actually pushing into hundreds of microwatts or sub-milliwatts level, which would be good to power many electronics, right? So this is the recent work done by my PhD students, and we can also develop into different form factors, right? Freestanding films, composites, and for example, here we also have done the continuous cycling test. We have done 25,000 cycles to demonstrate the output stability. We can also charge capacitor. And then we also recently integrated with the textile, right? Because we know that if you want to integrate with clothing, right, you want to have some fabric materials and then and weave it into structures. So this is actually a collaboration with Professor Tian Li from Peking University. And then we see that we have successfully integrated this PEDOT-PSS conducting polymer with fibers. And we also have successfully demonstrated different self-power sensing applications. For example, the sliding mode, the impact mode, and then you can also weave it into different structures, right? So basically, you can see that here, if you rub on the surface with another object, so here every, for example, the aluminum PEDOT-PSS nodes will give you one data point. So if you have a third objective on the top sliding lid, you'll be able to tell where this objective is. So this is a simple demonstration of different self-power modes, right, without any battery. So those are some recent results. We also quantified for example, the force tapping, and we come up with different mathematical models to testify, for example, the order of magnitude we can achieve for biomechanical force application. And we also recently demonstrated the slip detection for robotic hands. So which is something we didn't put it here, but we're working on the manuscript right now. So lastly, I have two more slides here that we know that in the solid thin film systems, we can generate DC. And then we also know that for chemistry catalysis applications, people actually use, for example, the so-called hot electrons to generate, to trigger chemical reactions, right? So one day I was asking my graduate students, can we actually use the same similar idea? And because we know that the collision or the mechanical interaction between semiconductor metals can generate high energetic hot electrons, right? So in this case, can we actually use it for chemical reactions? So we run experiments. It's very promising. Now you can see that when you have aluminum only, titanium only, and aluminum plus titanium, or with the same weights, we can see that if you only have aluminum in a solution, and then if you sonicate or you stir it without any lights, because we want to exclude the irradiation effects, there's no degradation of these dye molecules. This is in red colors, right? And then, but however, if you only have titanium oxide, it doesn't happen. But if you have the two materials together, you can see that it's a very significant degradation of these organic molecules, which is very exciting. We've done a lot for characterization, and then the conclusion we have is that by generating electron hole pairs at the collision interface between the metal and semiconductor, those electron hole pairs can further react with water to generate highly energetic or highly oxidative radicals, for example, OH radicals and O2 radicals. So those radicals can be demonstrated from the fluorescence spectroscopy. And we also have done the mass spectroscopy analysis to show this is not simply a physical absorption, but we indeed degrade it into different small molecules. So the last one I would like to show is the so-called tunable triboelectronic concepts, because right now one of the questions we have is that we know that for two metals rubbing against each other, it doesn't generate any electricity, right? If you have one metal versus one insulator, it gives you electrostatic charges. Metal versus semiconductors give you DC. But what if you have a tunable material, for example, a phase transition material like vanadium oxide, right? For a vanadium oxide, it does change its conductivity as a function of temperature. At room temperature, it's insulating states, and then when the temperature is increased up to, for example, a 60 or 70 Celsius degree, it will be suddenly converted into metallic states, right? And then we actually use this concept, and then you can see that with and without heating, there will be like 2 orders of magnitude DC outputs, right? When you have another metal sliding on the top. And then when it's cooled down, then the currents will return back to its original level. So we know that this is actually associated with the phase transition of these materials. And it's a tunable tribovoltaic effect, which might be used for future triboelectronic device applications, right? So we demonstrate a dynamic phase transition with a sliding heating probe instead of a heating stage. And then you can see that that phase transition can actually be triggered in nanosecond domain. So that's why when you slide it with seconds of time scales, you have sufficient time to trigger phase transition, and then at the same time, you can see that the power outputs can be enhanced dramatically. So, right, so this is the some new work we have recently done, which in collaboration with Professor Haiyan Wang in Purdue University and Professor Zhe Wang. The last one, I would like to give you this future perspective. I think this is a very nice summary and perspective by Dr. Sichuan Ling and Zhe Wang in their recent review paper published in Materials Today. And then basically to summarize the material, the observation, the material developments, and some of the future directions we can go to study this phenomenon. And also, I also added a few points here. That's something we can do in the future. Especially, I think the rich physics of semiconductor itself might give us many new exciting observation and findings and discoveries in the future. And with that, I'd like to thank all my hardworking students, all my collaborators, as well as the funding agencies. Without their efforts, nothing can be done in the group. And so this is going to be that's all for my talk. And then thank you so much.
Okay, thanks, Professor Niu, for his wonderful talk. I would like to welcome our next speaker, Professor Zhang Ming from Peking University Shenzhen Graduate School. Her presentation today will be flexible and stretchable electronics based on carbon nanotubes. I would like to briefly introduce Professor Zhang. She is an associate professor of electronics and computer engineering at Peking University Shenzhen Graduate School. And she also a deputy director of thin film transistor and advanced displays lab, and founder of Nano Electronics and Soft Electronics Lab. She is a senior member of IEEE. She received her bachelor degree and master of philosophy degree from the Department of Microelectronics and Solid-State Electronics at Xi'an Jiaotong University, and her PhD degree from the Department of Electronics and Computer Engineering at Hong Kong University of Science and Technology. She works for Solomon CTech Limited in Hong Kong for 6 years, developing advanced devices for displays technology and with relevant foundries. She joined Peking University Shenzhen Graduate School in 2020. In 2012, her research interests are focused on flexible and stretchable electronics, nanoelectronics, neuromorphic electronics, bioelectronics, as well as advanced displays. She has published over 130 peer-reviewed papers in one book and has been awarded 18 patents. She also served as a technical program committee member for several relevant international conferences. Okay, without further ado, let's welcome Professor Zhang Ming for her talk today.
Thank Professor Huang. Can you hear me?
Yes, I can hear you.
Okay, thank you. Ladies and gentlemen, it's my honor to share our recent progress on the flexible and stretchable electronics based on carbon nanotubes. I'm Zhang from Peking University, Shenzhen Graduate School. Okay, we know recently the AI is coming. Actually, it's coming at the year 2023, and at this era, we know that the Chat GPT combined with the mixed reality display, things like that, we will find that we have no choice but to hack the coming of the human-machine interaction. For the human-machine interaction, the requirement actually we need is real-time information interaction. We need to have the very accurate detection and faster response. We hope the system is very light and very mini and very light, is variable and easy to carry. And also we wish the system to be very low power because we don't want to bring a very heavy battery with us with a wearable system. And also, if the system has the edge calculation and has kind of intelligence, it will be even better. And for this system, to meet this requirement, the flexible and stretchable electronics is kind of very promising candidates. For the flexible and soft electronics, most of the time we'll use them for the wearable healthy monitor system. We know normally we will wear a watch or wear some wearable devices to monitor our physiological signals like the ECG, like the oxygen concentration in blood, like the motion morphology and the baby status, especially in the past epidemic of COVID-19. We know sometimes it's very urgent for us to measure the kind of the heartbeat signal and kind of the oxygen concentration in blood, but we cannot go to hospital. You know, with the aging, with the progress of the aging and also the low birth rate in our society and actually the global. The comprehensive medical monitoring at home is very urgent. Actually, there's no choice in the future. If we can have enough wearable systems or the wearable cartons around our body, actually we not only we can monitor our physiological electrical signal like ECG, EEG, and also the electromyographic signals. That is very urgent signals. Besides that, we can also measure the chemical signals like the neurotoxin. Sometimes somebody's got some toxic contamination, but he doesn't know it until very dangerous. So the long time and in situ neurotoxic detection is also very important. And also the glucose and the lactic acid, that kind of very important, very important the detectors for the long time healthy monitoring. Besides that, we can also monitor the ambient environment like the temperature, sound, and light, and also the body temperature, etc. If we have so many wearable tattoos stuck on the body, and if every tattoos and every system can do the in situ computation by themselves, then we can have so many AI on bodies. Actually, besides the wearable system, the soft electronics can also work very well for the human-machine interaction, combined with some advanced VR display, VR devices. If we combine the haptic sensors with the VR devices, actually, when you have the video talk with somebody, when you touch the screen, and the people, the person, if she wear the VR devices, she can feel your touch. And this kind of social media application will be very popular in the future. It's just like the switch, just the feel is just like the switch in the game. You know, I think most of you know the game, the switch. And also, if we combine the intelligence, combine the neuromorphic devices with the display, we can have the foldable display. The foldable display just use the flexible display as kind of scratch papers. And if we put that intelligent flexible electronics films on the prosthetic arm system, it can just work as an interface between the person and that machine. And then the sensor can feel something and pass a signal to the person, and then passes neuromorphic system and let the brain know, oh, it's hot. And if the flexible electronics and combined with that holographic projection, you may get this kind of video, get this kind of experience in this video. Actually, we can combine the haptic sensors with this holographic projection. so that we can simulate many different of the experience just at home or at lab. No matter it's for wearable devices or it's just for the human-machine interface, a software system integration is similar. We just need the input and output between them. We need the processing blocks. For the sensor part, I think most of us know is very clear. That's kind of sensors. We have various sensors for string sensors, shear sensors, temperature sensors, bell sensors, medical sensors, all kinds of sensors, and then we got the signals. But sometimes the signal is very small, or sometimes the signal is very noisy. So we need to process the signal to make it clear and larger to drive the load. In this case, we need the integrated circuit. We need digital analog circuit for processing and control. And this is based on the Newman system. And for the new system, as Professor Chai talked just now, actually we can have another a new kind of the processing system is artificial neuromorphic devices. With this system, we can get synapse devices, artificial synapse devices, and neuromorphic network, so that we can simulate or mimic the human synaptic transmission process. We can get the sensing, transmission, and computing in one devices. So no matter which one, it can make the signal better and then pass to the output, or sometimes directly feedback. For the output devices, normally we will make it some flexible or stretchable display, and sometimes we will make it kind of storage devices. So if we want to make various systems for different applications in the future, the first thing we can do is we just make some kind of some of the building blocks like Lego. So in today's talk, I mainly focused on our works for the digital circuit, transistor, and digital circuit, and also the flexible and stretchable synapse transistors. For the circuit, as I mentioned just now, we need the basic flexible circuit or stretchable circuit for the logic operation, and for the data storage, for signal amplifying, and for signal transmission. For this kind of circuits, we need to build both the digital and sometimes we need the analog circuits. And no matter which kind of circuits, the basic components for all kinds of circuits is a flexible transistor. And then in a flexible transistor, if you want to have a very ideal flexible transistor, first several requirements, including we want it is soft. It works high speed but low power, high integration with very high density. But it should be light and conformal, transparent, and it's better to be gas permeable, and it's better to be stable for long time work. To build a flexible transistor, first thing we need to consider is what is the active layer. As we may know, some of the promising candidates include the organic layer and the IgZO layer, metal oxide. I just take IgZO as representative. Actually, metal oxide is kind of a serious material. And the silicon nanowire, LTPS, and carbon nanotubes. For the organic, it has very good stretchability and flexibility, but the mobility is some low. And the metal oxide, we know it's a kind of material in the display industry. The mobility is okay, but for the banding and stretchability, for the very low reader, very small readers banding or the stretch transistor, that's a problem. For the silicon nanowire is still expensive because it's use silicon, and for the LTPS, because the temperature is very high, so it cannot work for the flexible and the stretchable substrate. Carbon nanotube is just kind of a balance between this electrical performance and the mechanical performance. So in our work, we mainly focus on the carbon nanotubes active layer. Beside the active layer, the gate dielectric is also a bottleneck to realize the soft electronics. Normally, people have two choices. One is in organic metal oxides. That one normally has good K value, so has good capacitance value, but it's fragile. And organic has good mechanical performance, but normally it's very its dielectric performance is some low. The two-dimensional materials is also used by some of the researchers. It's a balance between dielectric and mechanical performance, but forming a very good layer for the 2D material is not easy, especially for the flexible and stretchable material devices. We need the film. We cannot use the single layer film. We need the film formed by the powder by the particle. So it's not easy. So in our work, to form a good flexible devices, actually to form a good devices for any of the emergent devices, interface is everything. In our work, we need to focus on the carbon nanotube that active layer and the dielectric, the interface between them, and the other interface is a carbon metal interface. So we propose full carbon intrinsic flexible electronics. In this devices, we use semiconducting carbon nanotubes working as an active layer, and the metallic carbon nanotubes working as the source string electrode, and also the gate electrode. For the dielectric, the very good choice actually is the graphene oxide, because the channel, the electrodes, and also the gate are all carbon-based. If we choose a graphene oxide as a dielectric is also carbon-based, so that their interfaces between are very preferred. You can say if you use just a carbon nanotube and the graphene oxide, we can get kind of integration of the transistors array like this. For the metal carbon nanotubes and the semiconducting carbon nanotubes, the boundary between them is very clear because they are using different tubes, and the metallic tubes is kind of multi-wall, so it's kind of thick, and semiconducting carbon nanotubes is a single wall, just 1 point something, so the diameter 1 point something nanometers, so the diameter is very narrow, and the boundary is very clear. For this the total thickness of this device is just around 40 nanometer, because every layer is kind of a network or kind of the particle field, so it's very thin. But it's not easy to realize this kind of devices, because we know every layer of this device is carbon. That means it's a homogeneous layer. Since they are homogeneous, so you have no selectivity between when you do the etching. When you do the traditional photolithography and etching, you cannot choose some method to etching carbon nanotube, but without hurting the dielectric. So we propose a method called photolithography incorporated filtration. In this method, we don't need to do the traditional photolithography and etching. We just put the photoresistor on the substrate, and then we pattern the photoresistor to form the expected pattern, and then we peel off this photoresist and stick it down. Peel off this photoresist with the PET substrate. For the PET substrate, it's we can see here for the PET substrate is very porous. It has some hole. It has many holes on the substrate, and then we put this filtration film and the photoresistor with the pattern on this small filtration machine. Actually, it's a very small gadget, and then we just give negative pressure to filtrate different layer, every layer, different layer, like the semiconducting carbon nanotubes into this pattern, and then the pattern will leave on this PET substrate, and After finish the semiconducting carbon nanotube filtration, we'll remove the photoresist and form another layer for the source strain multiple carbon nanotubes, and then the graphene oxide, and finally the gate electrode. So we just repeat this process for four times, and then we got the final devices. These devices have a good electrical performance. You can see the linearity in this linear region is pretty good. The gamma is almost 1, and for different voltage, it can works from it can works at a very low voltage. Actually, just I think 30 milliwatt until 800 milliwatt. It still works good, and especially the mobility of this device. The mobility of this device reaches 300 something. It actually is very high for the flexible devices, and also it has very narrow hysteresis. Actually, you can just ignore the hysteresis. It's very clean, and the subthreshold swing reaches 51.8. It just exceeds the Boltzmann limitation. And why we can get this good performance? One is because from this charge density difference diagram, we can see the graphene oxides can get the electron from the carbon nanotubes and then leave more holes as carriers to transport. We know the carbon nanotube transistor is a p-type, and also from the electron localization function simulation, you can also see the bonding between the carbon nanotubes and the graphene is very weak, so that the bonding between them is kind of van der Waals contact. And we also measure the flexibility and the transparency, the statistics data, and also the inverter. Anyway, from the curves, from the data, you can see the banding reaches almost the smallest, but just here, it's very close to the smallest. Although we got very high mobility in that devices, but from the statistic data, you can see the variations is still some large. So that we will, if we want to continue to form the circuits, we will further improve the statistic data, and also we need to improve the integration level. So that we propose another method. We still use this all carbon frame, and then this time we use the polyimide aluminum oxide, the hybrid dielectric, work as the gate electric. And in this device, we can realize very good inverter, very good transistors, and with fairly good banding readers. But of course, this one is not so good as the previous one because the substrate is PEN. The previous one, the substrate is PET. But with this one, because the transistor has very good uniformity and narrow variation, so the circuit works very well. Like the inverter gets the highest gain, the record high gain reached the 342, and also the tensile string because we use PN substrate, the tensile string reaches the 3.1%. That's also the highest for the flexible transistor. And for the inverter, just a 50 milliwattage, it can work very well. Actually, it works in the subthreshold region, and the inverter can also work as an amplifier to amplify the small signal by 100 times. And we also use this platform to fabricate the real oscillator, the different logic gates. It all works very well. And further, we use this hybrid dielectric, combine the carbon nanotube transistors with the IG0 transistors to realize the 3D CMOS intrinsic flexible electronics. This one is still undergoing. Besides flexible transistor, we also realize some stretchable electronics. This one is not ours. This one is Professor Zhang from Stanford University. Professor Bach's work has the largest integration until now. They have 300 something transistor per centimeter square, and the total transistors for this small system is 6,300 transistors. It has very good integration, but the mobility for every transistor is still low because they use a coffin, that organic as active layer. The coffin is still the mobility is some low. So we still use this all carbon frame to form the stretchable transistors. We know because the carbon nanotube network has very good stretchability. So the only thing we need to find is a very high stretchability dielectric. So we use a polyurethane as a dielectric because it has good stretchability and also it has a high K value. And the realized stretchable electronics has you can just stretch it, twist it, and hook it is no problem. The even better performance is it can work at the negative 10 milliwatt VDD. And for this work, the most important point is the drivability reaches 810 μA per millimeter. This one is the highest until now, and the mobility 221 is also the highest for the stretchable transistor. This is stretchability. We measure it. Why we can do it? Because we propose a method called remove transfer photolithography method. We use IGZO as a protection layer, and finally, after we pattern the carbon nanotube, we just remove the IGZO. And you see the metallic carbon nanotube and this semiconducting carbon nanotube has even better resistance after this process. And also we remove the sacrificial layer so that the stretchability is also improved. Besides this traditional circuit, we also work on some neuromorphic transistors. For the functional neuromorphic transistor, I will not go in details because Professor Chai talked it just now. And the biggest property is the synaptic transistors. The artificial neuromorphic system. They can sensing, transmission, and perception together. The most important thing for this kind of a synaptic transistor is their dielectric. The dielectric, normally we have most of the people choose the three kinds of the electrolytes, either dielectric, liquid, oxide, and polymer. And the liquid one actually is not so stable in temperature limitation, so it's normally used for the sensor. And the oxide one is not easy for stretchability. The polymer has promising advantages for this kind of stretchable synaptic transistor application. So we propose to use a polyvinyl alcohol as a gate dielectric to realize the flexible and stretchable synaptic transistors, because it can produce a electrical double layer as a dielectric, and also this PVA is kind of biodegradable. It's very environmental friendly. And if you cut it, it can self-healing. If you burn it, it can self-healing. And the stretchability is good, and dielectric constant is around 6. That's also good. So that we use PVA to realize the flexible synaptic transistor, and further we use it to realize the stretchable synaptic transistor, especially it's with temperature responsive performance, and also it has a string performance. So we realized that this kind of devices, this kind of transistor, similar like our previous transistor, but with a special PVA dielectric here, and we can modulate the hydrogen bonds, the hydrogen density in the PVA to change their plasticity. And this the synaptic transistor, the performance of synaptic transistor before stretching, you can say that this is the normal measurement for the snap transistors, the kind of SVDP, SDDP. I will not go details here. The most important thing is the PPF is things like that. The most important thing is if we apply string to this stretch transistor, to this synaptic transistor, the learning ability or the plasticity will change. That can be modulated. You say different string will get different learning ability. And it is also similar for the post-synaptic current. You can see the similar performance. The main tendency is the higher the string, the learning ability is decreased. And we use this one for demonstration of the associative learning. Use a Pavlov's experiment. You can see with the string, if we have there's no string, the dog can learn the device. It can have the associative learning and can learn release the salvation on the bell very easily. But if we apply 50% string, the learning ability actually is decreased. Okay, the most important thing for this stretchable synaptic transistor is the temperature response. This is unique for this device. This is the first time to report the temperature response. And you can see from this excitatory or the inhibitory performance that the higher the temperature, no matter which one, the higher the temperature, the plasticity is improved. That means the higher the temperature, the learning ability is improved. The mechanism is because with the temperature increasing, the radius of the gyration for PVA is increased, so that the distance between the hydrogen bonds is increased, so that the proton can hop longer or hop longer and faster in this PVA modulated in this PVA material, so that the learning ability is increased. Here is also the detailed demo. Is when the temperature is increased, the learning ability is increased, and also we can combine the temperature and the string together. And one more important thing is when the temperature is increased to 70 degrees, the learning ability is increased and learning like this. And then when temperature is decreased to 50 degrees or to the 35 degrees, the learning ability will drop down back to the previous one. That's self-healing from birth, just like the skin. If we combine the temperature response and also the string response, we can get different combination for the learning ability, so that this artificial neuromorphic skin is very similar like the skin of a human. It can integration the sensing, and it can memory what happened, and it can have the real-time temperature response, and also it can be changed by the tensor deformation, and even it is burns, it can self-healing. Okay. Just now I mainly talks about our flexible and stretchable transistor and circuits, and the neuromorphic works mainly focus on this part. And besides that, we also work on some energy and sensor devices. And actually, I have some cooperation with Professor Jing Liu. And also, we dig some of the mechanisms in the new devices. Our target is finally we got a monolithic integration of the software system. Okay, I will thank my students for all their innovation and hard work, and thank my collaborators for their kindness and support, and thank all the funds, and thank all for listening.
Okay, thank you for the wonderful talk from Professor Zhang. Our next section will be the discussion section. I would like to invite all the speakers to open your video as well as your audio, so we can talk together. Okay, so actually, today's it is a Labor Day holiday. So first of all, I would like to thank all the speakers to attend this presentation. And I think all of you give our audience wonderful talks. I have a few questions to each of you. Maybe we can start with Professor Chai. Professor Chai, you actually mentioned about two kinds of transistor in your research. When you talk about low-level in-sensor computing, you mentioned two transistors. The first transistor is based on the 2D materials, and I guess the second one is also based on the 2D materials. What is the difference between these two transistors?
Basically, they are the same material. Both the channel material are both molybdenum disulfide. So regarding the difference, uh, it indeed has some difference. So from the first work, actually, we use the phototransistor to demonstrate the in-sensor vision adaptation. And from the second work, we still use a MOS2 phototransistor to show the in-sensor motion perception. So the major difference actually is the trap level. So in the first work, actually, uh, we uh, when we do the vision adaptation, we modulate the photosensitivity over a larger range. So here, actually, the trap level actually distribution is very broad. But in the second work, we just use the shallow trap charge trapping to modulate the time constant. Then we can capture the motion at different speeds. So basically, the device structure are exactly the same. The only difference is the interface charge trap level. So the first one, the energy level distribution is very broad. The second one is just very shallow. Because the shallow trap, its charge dynamic is very similar to that of graded neurons. I hope I answer your question.
Okay, great. So, following question is that for both devices, I guess you need to scan the gate voltage. The first one, you need to scan the gate voltage from the negative value to a positive value, and for the second one, maybe you also need to scan the gate voltage. But it seems that the first one responds, to say the speed is relatively low because it's only for still image, and the second one is for the dynamic images. So, so are there any difference between the circuits you use to drive these two sensors?
Uh, y- yeah, you ask the very key points. So from the first demonstration, actually, the adaptation process actually takes a relatively longer time. It takes hundreds milliseconds at even tenths of seconds. So it's a long process. But this process is still comparable to that of human vision system. So we are trying to increase the adaptation speed. For example, we are going to design and fabricated some PN junctions. In the PN junction, it has built-in electrical field. It can separate the electric and hole very quickly. So in this kind of structure, we can expect the adaptation speed can be increased. We are still working on this. For the second device, actually, uh, we can perceive the motion with a very different speeds. So, for example, in the last slide I show you, we can perceive the motion of a snail, which moves very slowly. We can also perceive the motion of a panda. So, because from the shallow trap charge, we just use a very small gate voltage. We can tune the time constant over a larger range. So from the second work, actually, we like the shallow trap charge, which allow us to perceive the motion with a very different speeds.
Okay, great. Thank you. So my next question goes to Professor Liu, because I noticed that you actually studied triple electronics effect and different kind of triple electronics effect in either in both micro scale and macro scale. In the micro scale, you use the 2D materials, and you in the macro scale, you use some conventional semiconductor materials such as silicon and gallium nitride. So I just wondering, can we just use the 2D material in the macro scale as well? So if we cannot do it right now, how can we bridge the gap to ensure us that in the future maybe we can use the 2D material in the macro scale?
Sure. Thank you very much for the great question. So as a matter of fact, we have already demonstrated 2D materials for macroscopic demonstration. I didn't touch that much, but yes, we have already demonstrated, for example, with single crystal MOS2, which is like in the multi-layer forms, and then basically we showed that when you have a single crystal MOS2 multi-layers rubbing against other metals, it can generate the same phenomenon with DC outputs. And I think, like what I mentioned, there's some other groups right now, they have demonstrated, for example, the doped diamond and versus some other, super break materials, like 2D materials. And so, yes, so I think right now it has been demonstrated. And then the next question is, for nanoscopic level, we have this well-defined 2D layers propelled by CVD and things like that. And for macroscopic level, I would say, since you mentioned the gap, I think the gap would be what would be the form factor of these 2D materials in the real applications. For example, people have been using 2D materials as a mechanical joints. Right, and then it has been used as a solid lubricants for many applications. Well, liquid lubricants cannot be used, like in the aerospace applications. Well, for spacecrafts, these liquid lubricants cannot be used. They have to use something like MOS2 or graphites, right? And then for those places, we know that there's already metal MOS2 contacts there, right? Exactly. Can we actually take advantage of the existing material system, right, and then achieve some sort of in mechanics self power sensing, right, with those materials? I think those can be good direction to explore and has significant implication for many applications, right, like for aerospace and many other things. So, but of course, if we want to come up with like nanoelectronic concepts, for example, can we actually use for some of MEMS structures, right? Like scaled up MEMS structures. I think that's what involves the design of structures and also the mechanical structures as well as electrical structures. How can we achieve that electromechanical response? Right? I think there have been some efforts working with for example, piezoelectric array, right, based on MEMS techniques. Can we actually use similar concept for these 2D material-based DC outputs, right? And then for example, to do, different frequency and also different application sensings. So yeah, that would be my answer.
Okay, thank you very much. The next question goes to Professor Zhang. Since I noticed that you actually use a very brilliant idea to fabricate the transistor using some kind of filter and the spray coating approach. So I just wondering that so when you do the spray coating or when you are using the filters, so will the dimension of the filter will be what will be the ratio of the dimension between the filter and the device you are going to get?
Thank Professor Huang. You mean the feature size, or mean the?
Yeah, the filter size because it looks like it is a projection. It is some kind of projection approach. So I will assume that the filter may be smaller compared with the feature size, the practical feature size on the device, right?
Yeah. For the filtration, actually, you mean that's kind of a contact liner. Actually, we are use contact liner. It's not projection. So the feature size of the the feature size of pattern is similar as the pattern in that in the photoresist and the mask. The feature size for the filtration, we can reach around 5 micron, and for the photoresist is also 5 micron to 10 micron.
Okay.
Okay.
So my second question is that in your last work, you just mentioned that you using PEM as the
Hello. Sorry, can you hear me? I suddenly cannot hear any voice.
I think you're good. I think probably because of the internet from Dr. Huang's side.
Provide some guidance for the audience how to select the dielectric layer.
Okay. Sorry, Professor Huang. Just now, what you said, I cannot. With every of us cannot hear it just now. Can you repeat the question? The network problem, maybe. Professor Huang. Does that mean offline or? Professor Huang, sorry, just now what you said, we cannot hear you.
Well, we're waiting for so we can continue the discussion.
Okay.
Yeah. So I think it's a wonderful to see the recent progress of these artificial skins and things like that. So one of the question I have is that suppose in the future you have a large area of artificial skins, which is conformal to, for example, robotic body or human bodies. How would you envision the future power strategy or energy strategy for this large area devices? Because right now I have seen like small area for demonstration or prototype which is connected to a cable or a battery or something. In terms of like distributed sensors everywhere, like how would you imagine the future power strategy?
Yeah, that's a very good question. Actually, kind of depending on the triboelectric generator and also the solar cell system. Just for me, in my thinking, until now, I just can propose this kind of the solutions. Yeah.
I see. I see.
Yeah, that's why also we work on kind of the energy harvester kind of things like that. We want to have some flexible energy harvester, to solve the problem. Yeah, we cannot carry battery. Okay,
I see.
Professor Huang.
Huang, yeah. So I think
Welcome back.
Dr. Huang is back online. Yeah.
Can you hear us? It's still not movable, it seems.
No.
Okay, I send message. Okay, we may continue the discussion before Professor Huang comes back. Yeah, just now for Jun's question, I'm also thinking, do you have any new idea or any preference actually for this solution?
I see. Yeah, yeah. Well, this is so. If you look at the energy, available energy sources we have, there are many different things, right? I mean, if you look at how nature works or how human body works, it does send energy from, for example, chemical reactions, right? I mean, there are many, say, ATP type of reactions in your body. So I'm thinking about some sort of Internet of Energy concept as well, not just from one source, but also from different sources. And then those energy can also be, can interact with each other. Energy sources can interact with each other in a more synergetic way to drive these type of, distributed units. And yes, and this has been miniaturized. And then, yeah, and I also think that some sort of a power management work also has to be done in order to optimize the energy efficiency, right? Like of different parts, and also to optimize, for example, the duty cycle of sensing and then wireless communication, for example.
Yeah, we use some of the circuits. Yeah, use some of the circuits for the power management.
Yeah. I think that part is also important. Yeah, I think Dr. Huang is
coming back
online. It's on and off probably. Yeah, but I mean, we can continue the discussion. I think Dr. Chai, I think it's wonderful to see the sensing work with the for the vision, the artificial vision sensing. I actually also have a question about, like, this is a long time question I have, is about the smelling. Actually, this is something people don't really understand so far. I mean, it's for example, if you think about a dog who can smell, who has a much better smelling capability compared to humans. This is actually very interesting, because if you consider the available density of molecules in the space, it's actually not that much. I mean, the same for the human and same for the dog. But I'm also wondering, like, is there any way a human body can do something, or can we do something to simulate smelling? I'm probably just a random question.
Yes. This is a very straightforward question. Actually, in this research field, some research already demonstrate neuromorphic from computing from the smelling. So, so why a dog have a much better smelling than human? That is because from the dog has a lot of neuron in their smelling system, but from people,
okay,
we have very few neurons. So if you have more neuron, you can do more computing. So
I see.
Yeah. So basically, from the smelling, it is a chemical sensor.
Yeah.
So chemical sensor or gas sensor, as long as you can use some hardware device to extract the information, and you fit this information into the artificial neural network, you can do the computing. Depends on different application scenarios.
I see.
Yeah, my interest is vision, because vision actually it occupy over 80% information for human.
I see.
So smiling, vision information is a data-intensive application, but for the smiling, actually, it's only very few data compared with the vision.
Gotcha. Okay. Thank you.
Professor Huang coming back.
Yeah.
Okay, Professor Huang, you may repeat your question you mentioned just now. We can continue. Cannot hear.
Yeah, I guess his network is not good.
Yeah. We still cannot hear you.
Professor Zhang, I noticed you show one PPT slide, probably slide 13. The subthreshold is even below 60 milliV per decade. So what's the reason?
Okay. That junction, that metal semiconductor junction, it actually is by the semiconducting carbon nanotube and the metallic carbon nanotube. And then that contact is not formed by Shockley barrier or Shockley contact or ohmic contact, that kind of van der Waals contact. For the van der Waals contact, there's only tunneling, or mainly by tunneling. So that is not the thermal ionized, not the thermal emission. The carrier just not passed by thermal emissions, mainly by tunneling. So that we can.
What's the gate dielectric is?
The gate dielectric, that one of the gate dielectric is a GO, the graphene oxide.
Yeah, so it's not a negative capacitance effect.
You mean the negative capacitance effect?
Yeah, so because the GO is not ferroelectric, so I suppose the low SS is not from a negative capacitance.
Yeah. Let me think. In our opinion, in our discussion, I think it's we just analyze the tunneling. We measure some of the temperature, the electrical performance on the different temperature to say that the tunneling is works for mainly for that mechanism. You mean the main reason is from the graphene oxide?
Yeah,
or
basically from the so recently NC-FET negative capacitance transistor is a the research topic because I'm just wondering. So the physics mechanism. So if it seems it's a tunneling transistor, not an NC-FET.
At least we understand it as a tunneling transistor. Maybe we need to analyze whether the negative capacitance involved in. But traditionally, the GO may not be. Okay. Anyway, we will go details. To check it.
Okay.
Okay, Professor Huang, welcome.
Okay. So so you can hear me now, right?
Yeah, sure.
I think we have one time for the one last questions from the audience because the audience asked Professor Chai questions. In your second word, motion recognition should be related to speed. And what is the fastest moving speed that can be monitored by this work? Is there any comparison between the speed that can be monitored by human eyes?
Yeah, this is a very good question. Very good question. So actually, if you notice our video, actually we show a movement of a ball. So but the speed of this ball actually is not very fast. The absolute speed is just, I guess, just a few kilometers per hour. So the question is, what's the maximum speed? It really depends on the device response characteristics. So we didn't push the limit. So we at the current stage we still don't know what's the maximum speed we can capture using our device. But I think it's very related to the decay, the time constant of the decay process. So if the photo current can be decay within, so in our work actually we have one slide showing how to measure the time constant. The minimum constant actually is 1 millisecond. So if we convert this time constant into speed, we should have a rough value. But it's still very dependent on the our testing equipment. We didn't push to the high speed, so here we just show how to extract the motion feature. But this is a very good question, so it's very deserve for us to continue this direction. Thank you very much.
Okay, very good. So due to the time issue, so we are going to start a discussion session right now. Maybe for the audience, if you have more questions, you can just email these three professors to ask your questions. So let's go to our next section. I would like to give a certification for our three excellent speakers today. First will be Professor Yang Chai. Thank you for your talk in sensor computing for artificial vision. Very wonderful talk. Thank you.
Thank you.
And okay, and our next certification will be given to Professor Liu Jun. Thank you for your talk about mechanical modulated semiconductor interfaces, energy sensing and beyond. Thank you for your support of Yang talks.
Thank you so much.
And the last certification goes to our last speaker, Professor Zhang Ming. Thank you for your talk about flexible and stretchable electronics based on carbon nanotubes. Very wonderful talk. Thank you.
Thank you. Thanks, Professor Huang.
Okay. So for the presentation next week, Yang's talk, we are going to talk about advanced biosensing technology, and stay tuned. See you next time.
不再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌，不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can。没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最 造奇迹。我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可